Let's set up a new example. Consider the set S. S is a capital S. That's going to be the name of this set. And S is going to be a set of 3 vectors. The names of the vectors are V1, V2, and V3 because we don't come up with clever names for things in math class. This is why I can't have kids, because it would be like kid 1, kid 2, kid 3, kid 5. And people would be like, well, what happened to kid 4? I'm like, well, we don't talk about kid 4. I'm just kidding. I don't have kids, and I come up with actual names for my dogs. So I don't have kids anymore. I'm just kidding. I never had kids, is the story we're going with. I'm just kidding. What are we talking about? Oh, yeah. S is a set containing just these 3 vectors. And I wanted to write this down to make a note that we use curly brackets for sets. So curly brackets in math just means this is going to be a set. Also notice that the elements of the set are separated by commas. Things in a set are separated by commas. Elements of the set are separated by commas. It's going to, this curly bracket separated by commas thing is going to be important when we start making distinction between sets and matrices. In terms of vector names, when we're typing out vectors, usually we go with bold. Actually, we go with bold and non-italic. When we're typing vectors, unless I'm typing them in Canvas, because it's a kind of a real pain to type bold in Canvas if I'm having to do like in the equation in LaTeX. It's awful. But when we're writing, I don't have a bold-faced pen, so I just put a line over the top of it. A lot of times you'll see an arrow over a vector, and I'm just too lazy to write a whole arrow, so I just put a line over the vector. So that's just our notation. We just do a line over for written vector names. We want to make sure we distinguish vector names from scalar names. So that's the important part. We need to distinguish between vectors and scalars. Scalars are just real numbers. They can be actually elements from any field, but we're early in your math career. We don't know what a field is. They're the real numbers. If you start thinking, well, could it also be the complex numbers? Totally, it could be any field. But we want to distinguish between vectors and scalars. So I'll have something that says like x1, v1. X is going to be italicized and no line over it, so that x is a scalar. And v1 is a vector. So in this case, x1 is a scalar, and v1 is a vector. So that's why we want to write them different, so we can tell them apart. So S is the set of vectors v1, v2, and v3. I'm going to let B is going to be different. So I'm going to say let B be the vector -3, -2, 13. Now I'm going to write the same question a bunch of times in different forms. A question, now that given this setup, I got a bunch of vectors and I got a vector not in that set. So the question becomes, is B a linear combination of the vectors in S? Is B a linear combination of V1, V2, and V3? So that is a question that you might see on some kind of quiz. Is B a linear combination of V1, V2, and V3? What this means is that can we build the vector B out of the vectors V1, V2, and V3? That's another way to think about this question. So that is, can we build B out of V1, V2, and V3? This is equivalent to asking the question, is the vector equation x1 v1 plus x2 v2 plus x3 v3 equals B consistent? Is there some combination of x1, x2, and x3 that will make this a consistent equation? If the answer is yes to the vector equation being consistent, then that would mean that B is a linear combination of those vectors. We can build B out of those parts. Then if the answer is yes, we have the follow-up question. If yes, then how? That would be asking, find the general solution to the equation. So the follow-on question would be, if yes, then how? And that would be saying, find the general solution. Right now, these are the questions that I'll be asking. When I say solve this linear system, augmented matrix, reduced or echelon form, general solution. Is this vector equation consistent? Linear system, augmented matrix, reduced or echelon form, general solution. All right, let's find out. So let's take a look at this vector equation and write it out with the numbers in it. So we want this vector equation, x1 times the vector v1, which is 1, negative 2, 3, plus x2 times the vector v2, which is 2, 0, negative 5, plus x3 times the vector v3, which is 0, 4, negative 11. And I want this to be equal to negative 3, negative 2, 13. There's the vector equation that we want to solve. Here we're making a linear combination of the vectors v1, v2, and v3, and we want to see if there's some linear combination of these three vectors that will make the vector B. So there's our vector equation. This vector equation is equivalent to the linear system. So the linear system will be x1 plus 2x2 equals negative 3. Then negative 2x1 plus 0x2 plus 4x3 is equal to negative 2. And 3x1 minus 5x2 minus 11x3 is equal to 13. So here's our vector equation. Here's our linear system. If the linear system is consistent and the vector equation is consistent, then B is a linear combination of those three vectors. So we want to solve a linear system or vector equation. The way is to write the augmented matrix. So now we'll translate to the augmented matrix. The first column will be 1, negative 2, 3. Let's get rid of all this x1, x2, x3, and equal sign noise, and just write down let's remind ourselves that we're making an augmented matrix, even though I just wrote that up here. Now that we have an augmented matrix, this should just make us write the reduced row echelon form. Next thing to do would be to write the reduced row echelon form. So let's do that. I'm going to review the reduced row echelon form process. So sorry, TI-84, take a break. Oh, I wanted to do that one. I'm just kidding. I don't actually talk to my calculator. Shut up, yeah, you do. What are we talking about? No, not the class, I mean the calculator. Yeah, we'll talk about that later. So I will need to start in the upper left corner and see, can I do a pivot there? And the answer is yeah, there's a 1 there. Remember that the pivot process is get a 1 and use the 1 to zero out the column. Then move left and down until you're all out of pivots. So I'm going to do 2 times row 1 plus row 2. 2 row 1 plus row 2 is my new row 2. So 2 times row 1 is going to be 2, 4, 0, negative 6. I'm going to add that to row 2, and that's going to be 0. That's what I want. 4 and 0 is 0. 0 and 4 is 4. And then negative 6 minus 2 is negative 8. Row 1 isn't changing yet. Now I also need to get a 0 in the first column, third row, first column. So to do that, I'll do negative 3 times the first row, negative 3 times the first row, and add that to row 3. So negative 3 times the first row, I made a mess here. Negative 3, negative 6, 0, 9. Negative 3, negative 6, 0, 9. I'm going to add that to the third row for my new third row. Negative 3 and 3 is 0. Negative 6 minus 5 is negative 11. 0 and negative 11 is negative 11. Whew, saved it. And 9 and 13 is 22. And now, right now, we should be super suspicious. 4, 4, negative 8, negative 11, 22. We've got extra equations here. One of these equations is a combination of the others. If you don't see that right now, that's okay. We're still just trying to learn stuff. So this first column is done. That means I can't use that first row to get 1s anywhere. I go over to down to the second row and over to the second column and see if I can pivot there. And so my next pivot is this 4. So that I'm going to do a 1/4 row 2. That's going to be my new row 2. Row 1 is not going to change yet. If you're thinking I'm writing too many steps, that's okay. That just means that you see where this is going already. You're already building this skill. So my new row 2 will look like 0, 1, 1, negative 2. Now I'm going to use row 2. I've got a pivot in the second row, second column. Remember, the pivots don't belong to the values. The pivots belong to positions in the matrix. Now I'm going to use this one to get zeros above and below. We can see that if I take just 11 times row 2 and add it to row 3, I will get a 0 in the third row, second column. So I use this one to get zeros above and below. So we can see that if I do, let's say, I should do it here, but I'm going to try to conserve space. If I just multiply the second row by 11/4 and add it to row 3, I can see that I'm going to cancel this row out. I get that row of zeros. Oops. Remember, this does not mean anything on its own. Never say this happened because of a row of zeros. We never get to conclude based on a row of zeros. It doesn't mean anything for the solution set. Next, well, actually, let's stop and look at what we've got here. We can see that we're not going to be able to pivot in the third column. And since this is an augmented matrix, we can see that the rightmost column is not going to be a pivot column. That right there tells us that we're going to get a consistent system or a consistent vector equation, because the augmented matrix does not have a pivot in the rightmost column. This is a phrase that you'll see sometimes on my solutions for the homework. If you invoke the rightmost column, you have to be talking about an augmented matrix. So putting rightmost, even if it's the last column in a regular matrix that's not augmented, don't say rightmost unless you're talking about an augmented matrix, because you're going to start to get confused. So just be very clear about the things that you're talking about. I say this because y'all are new to this whole matrix game. I don't want you to make some noob mistakes, you know. So I still need to get a zero out the rest of this column, even though we know that there is going to be a solution. Our answer to the previous questions is yes. So I need to do, looks like -2 times row 2 plus row 1. So I'll do -2, oops, up here, -2 row 2 plus row 1. So that's going to be 0, -2, -2, 4. I'll add that to row 1, and that'll become 0 and 1 is 1. -2 and 2 is 0. -2 and 0 is -2. And then 4 minus 3 is 1. There's my new row 1. Row 2 can stay the way it is. And row 3 can stay the way it is. Let's remind ourselves this is an augmented matrix. Let's remind ourselves of where the pivots are. Now we can see that there are no more pivots. I've done the first row, I've done the second row. The third row couldn't have any pivots in it. So now we have an echelon form. We see that in each pivot column, there's a 1 in the pivot position and zeros everywhere else in that column. So now we know we're looking at the reduced row echelon form. So here are the things that we note. First, I didn't plan this very well because I ran out of space. So let's flip the page and write how we make our conclusions. So let's see, this is still. Labeling pages, more of that riveting YouTube. Make sure you smash that like and subscribe button. Which, since it's a linear algebra YouTube channel, you'll probably smash the like and subscribe button because you'll fall asleep and your face will hit the keyboard and all of a sudden you're subscribed to linear algebra and you're wondering why you get all these notifications. So what we noticed is that the rightmost column of the augmented matrix, so this is us thinking now, we're looking at this augmented matrix. I already forgot what it was. So what we notice is that the rightmost column of the augmented matrix is not a pivot column. Therefore, the system is consistent. So since the rightmost column of the augmented matrix is not a pivot column, the system or the linear system or the vector equation is consistent. Therefore, B is a linear combination of the vectors v1, v2, and v3. Now the question is, since the answer is yes, how? To get at the how, we need to write the general solution. And then we're going to take the general solution and write it in its parametric vector form. So let's take a note to write the general solution. We need to identify our basic variables and our free variables. The first column corresponded to x1, second column x2, third column x3. This is an augmented matrix. There's no x4. This was our constant column. I usually use K for constant. I like using the mortal constant because then that makes the song play in my head. Right? Like I can tell some people once I said mortal constant, some people are like all immediately so you're welcome. Or I'm sorry. So x1 and x2 are going to be basic variables, and x3 is going to be the free variable. We have one free variable. So we had a consistent system with infinitely many solutions because we had a free variable. So let's write down the equations. This says, first row says x1 minus 2x3 is equal to 1. And the second row says x2 plus x3 is equal to -2. Let's take these equations and write the general solution, which means solve for the basic variables in terms of the free variables. I like to lead with my constants because the constants are the place to start. So I'm going to say x1 is 1 plus 2x3. x2 is equal to -2 minus x3. And I'm going to make a note that x3 is free. Always just write your variables in order, x1, x2, x3, x4, x5, just top to bottom. When you hit the free variables, just write is free to make sure you get them all. When I write x1 equals 1 plus 2x3, I have implied that x3 is a free variable. But we're new at this. I need to know that you know that. When I talk to my colleagues, I don't worry about making a note that x3 is free. I know they'll get it. But you don't get to do that yet. So you have to write your free variables. So here's our general solution.
I have a question. So I just didn't get that how the x3 is free.
x3 corresponds to the third column in the augmented matrix, and the third column does not have a pivot in it.
Oh, okay.
The non-pivot columns are what correspond to your free variables.
Gotcha, thank you.
The question also came up, man, are we going to have to do this by hand? And no, this is how we're going to find the reduced echelon form. I want you to be able to do this process because that's part of it. If we don't do the process and get to the reduced echelon form, then we start making mistakes when we write the general solution. So we'll want to know what the process is like. But in an actual problem, I'm not going to be able to do this without smearing things. In an actual problem, we would just grab our calculator, go to second matrix, go over to math and go to it's B, and then brackets for the matrix, brackets for the first row, and then just punch in the matrix, 1, 2, 0, -3. Close the row, open the next row. -2, 0, 4, -2. -2, 0, 4, -2. Close the row, open the third row. 3, -5, -11, 13. close the row, close the matrix, close the command, and then proofread, but I didn't do that. I just got lucky. There's a picture in the files, TI-84 in action, that shows you what the syntax needs to be. So just copy that. Then you just have to remember where the reduced row echelon form command is, and it is in the matrix menu under math. So second matrix, math, and it's all the way down at letter B. Reduced row echelon form. You want that one, not the REF. You want reduced row echelon form. So what this is telling us is that there are an infinite number of ways to write B as a linear combination of V1, V2, and V3. So note. We can write B as a linear combination of V1, V2, and V3 in an infinite number of ways. One for every value of x3. So if x3 is 0, here the general solution is x1 is 1 plus 2x3, x2 is -2 minus x3, and x3 is free. So one of the solutions, let's write down some solutions. If x3 is 0, then x2 is going to be -2, and x1 is going to be 1. So what that means is that 1v1 minus 2v2 plus 0v3 should equal b. Every choice of x3 will lead us to a solution. So if I choose x3 to be 1, if x3 is 1, then x2 is -2 minus 1, or -3, and x1 will be 1 plus 2x3, or 3. So what that means is that 3v1 minus 3v2 plus 1v3 is equal to b. That's another way that we can write b as a linear combination of the vectors v1, v2, and v3. And this goes on forever because we only have 3 choices: no solutions, exactly one solution, or infinitely many solutions. So I could choose x3 is equal to 100. That means x2 is equal to -2 minus 100, or -102. And x1 is 1 plus 2 times 100, or 201. And what that means is that I did not give myself enough space, but 201 times v1 minus 102 times v2 plus 100 v3 is equal to b. We can check this. We have the vectors v1, v2, and v3. I'm going to check this one in the middle, just to pick one. So v1 is the vector 1, -2, 3. So if I take 3 times 1, -2, 3, this is very dangerous because I just did arithmetic and now I'm compounding arithmetic on top of arithmetic, and I'm not very good at arithmetic. So I hope this is the right solution. Let's see, I get 3 minus 6 plus 0. Then I get -6 plus 0 plus 4. And then 9 plus 15 minus 11. So 3 minus 6 is -3. -6 plus 4 is -2, and 9 and 15 minus 11 is 13. So it works. B is a linear combination of V1, V2, and V3. Here is a linear combination of V1, V2, and V3 that is equal to B. Here's another one, 1, -2, 0. The next thing that we want to be able to do is we have these values, x1, x2, and x3. And so there's just 3 different numbers that are all related. And we know that vectors are just columns of numbers. So I want to write the general solution in a parametric vector form. So if I have this, I'm going to take my general solution. X1 is 1 plus 2x3. X2 is going to be -2 minus x3. When we say x3 is free, we don't ever write it this way, but we can think of just x3 is just x3. This is what we do with our free variables. This is just when we have a free variable is going to free variable. Hater is going to hate, x3 is going to be equal to x3. So we can think about x3 being free as x3 will be written as 0 plus 1 x3, which is what I really wanted to write. Now I'm going to write the parametric vector form of the solution. I'm going to say, as a vector, x will be equal to, the constant is 1, -2, 0. Plus x3 times the coefficients of x3. x1 has a coefficient of 2 for x3, x2 needs a -1, and x3 is just x3. So this is the parametric vector form. So here are now 2 ways that I can ask for the solution to a system or a vector equation. I can ask for the general solution, or I can ask for the parametric vector form. 2 ways we can write our solutions. Note that if x3 is equal to 0, then the vector solution is 1, -2, 0. 1, -2, 0. That's how we build B. If x3 is equal to 1, then I get 1 and 2 is 3, -2 minus 1 is -3, and 0 and 1 is 1. So writing x3 is free, and I could write x3 in terms of itself. That would just be no constant plus 1 times x3. That's because x3 is our free variable. I wanted to be able to see it as 0 plus 1 x3 in the parametric vector form. X3 just gets to be itself. That's just what we do with free variables in the beginning so that we can see how the parametric vector form is going to drop out. So this seems like a lot to remember. Don't worry, that's only because this is a lot to remember. But don't worry, all you have to remember is all of it, all of the time in perfect detail. Oh, wow, that seems kind of a lot. So if it starts feeling like it's a lot to remember, that's only because it is a lot to remember. But that's why we practice.
I have a question.
Yes.
So what I mean that how x1 and x2 become x?
Oh, x is just how we would list x1, x2, and x3 all together. I want to take, since there's these 3 components, I'm just going to take these three components and give them the name, the vector x. Notice I got a bar over the top. So I'm taking x1 and x2 and an x3, and I'm grouping them all up and calling them the vector x.
Gotcha. Thank you.
Any other questions? All right, let's pause the video here and think about where we need to go next.